Okay, theorem 1.5 says the following. Let AN be a bounded sequence. So it has an upper bound and a lower bound. If all convergent subsequences converge to the same limit, then the sequence itself is convergent. And without saying it in the theorem, it should be obvious that they converge all to the same limit. Because remember, AN is a subsequence of itself. So if it converges to the same limit, it converges to the same limit as all of the subsequences. They'll all converge to the same limit. So this is a one-directional proof. We don't have to do an if and only if. So we start with a bounded sequence. If all convergent subsequences converge to the same limit, that's going to be our hypothesis of the proof. We're simply going to prove, if that's true, that AN is convergent. So to start the proof, I want to define a number A to which the subsequences converge. So let's suppose all convergent sequences, subsequences, converge to the real number A. I'm writing a little smaller because I've got quite a bit to write in here. I want to get it all on one board. All right, I'm going to make a note here. It's not really part of the proof, but it's important. In your homework, you will prove that one such subsequence exists. At least one such subsequence. And I'll refer to that again in this proof later on, down at the bottom. So in your homework, you are going to prove that if AN is a bounded sequence, that it has at least one convergent subsequence, even if AN itself is not convergent. Okay, well, we have to show that AN converges, and specifically, we're going to show that AN converges to A. It wasn't stated in the theorem, but we discussed this. They all have to converge to the same limit. We must show that AN is convergent, and we'll show that it converges to A. All right, this is going to be a proof by contradiction. So I'm going to say, suppose this isn't true. I'm going to say to the contrary, suppose AN does not converge to A. Thus, based upon what we wrote on the board just a couple of minutes ago, there exists an epsilon greater than 0 such that there does not, let me see, such that there is no capital N where the following holds true. N greater than cap N implies AN minus A is less than epsilon. Okay, it's a little bit wordy, and maybe I could have made that slightly more clear, but let's think about that. Since AN does not converge to A, there exists an epsilon where it's going to fail. And for that epsilon, there is no natural number in existence where, for every natural number greater than that one, that this is a true statement. So that's the negation of what it means for AN to converge to capital A. All right, So, for capital N equal 1, the index of the first element of the sequence, there exists a lowercase n1 greater than 1. That's because n is capital 1. And an minus a is greater than or equal to epsilon. Must be true. And I'm going to write out 2 more of these. And for for capital, in this case, for capital N equaling this N1, I just want a number bigger than N1. Well, actually equal to N1, we'll see why. I mean, we'll get the greater than over here. For N equals N1, there exists an N2 that's greater than N1, and a N2 minus a is greater than or equal to epsilon. Well, I guess I left off the subscript on that one. I'm going to write one more. For n equal N2, there exists an N3 that's greater than N2, and a N3 minus a is greater than or equal to epsilon. We can continue this process forever. And I'll write that down. I'm running out of room, so I'm going to continue over here. We repeat this so that for every k in the set of natural numbers, there exists an nk which is also in the natural numbers, such that the following holds true. Let's see. Repeat this so that for every k in the natural numbers, for every nk, there exists an nk in the natural numbers, and a finite sequence. And the sequence is just n1 less than n2 less than n3, all the way up to less than nk. And the distance between a, ni, and cap A is greater than or equal to epsilon for I equals 1, 2, up to k. So we're creating a subsequence, an1, an2, an3, dot, 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 where each element of that sequence is farther away than epsilon, or at least as far as epsilon, away from this sequence limit A, defined up here. So to finish this off, we would say the subsequence A sub n I, where I goes from 1 to infinity, that we defined right here, is bounded, obviously, because an is bounded. And has a convergent subsequence. Converging to a number different from A. And that's a contradiction. Sorry, getting sloppy down there at the bottom. In this final sentence, I have one more just to kind of close off the theorem. But in the last sentence that I wrote, we again used this homework problem. Every bounded sequence has a convergent subsequence. In this case, we're talking about a subsequence. But a subsequence is a sequence. If that subsequence has a bounded subsequence, call it a subsequence if you wanted to. Well, it must, because it is a sequence and it is bounded. So I'll finish it off by just saying, therefore, AN converges, well, AN is convergent, and more specifically, AN converges to A.
Do you have to include both parts of that sentence? You have to say AN is convergent and AN converges to A, or can
Nope.
you just say AN converges to A?
AN converges to A. I only did it that way because the theorem says that it's convergent. So that and it converges to A is just additional information.
Well, would it be just as equally correct to say, therefore AN converges to A?
Yes. Yep. Or it is convergent. Either way. You don't need them both, for sure. So we constructed this sequence. I think this is obvious that, the pattern that you're doing to continue here in capital N, for capital N equal to N3, there's an N4 greater than N3, and so on. In theory, to prove that this subsequence existed, it might have been nice if we used an induction proof, but it's so trivial, I didn't include that. An induction proof showing that each one of these, for all k, an induction proof for k equal 1 being the base case, and so on. Here's k equals 1.